Okay, so thanks everyone for tuning in. Today we have Vedika Khemani from Harvard, who's going to tell us about a combination of papers on many-body quantum dynamics, Hilbert spaces, local constraints, and all sorts of things. So Vedika, thank you very much, and the floor is yours.
Yeah, thanks, Ro. Thanks very much for the invite. This is my first time doing a virtual seminar, and it's a really great idea, so I'm excited about the opportunity to try it out. So as Ro said, today I'll be telling you about some recent work in the set of papers, mostly focusing on the latter one, on many-body dynamics in constrained systems. And, at the broadest level, this topic connects with the theme of much current interest in many-body physics, namely the study of unitary dynamics. So, just a question: is my title hidden by the video, or is that only on my screen?
We see unitary quantum dynamics up at the top.
Okay, so nothing. So you don't have any part of my slide hidden, correct?
I don't think so.
Okay, great. And okay, so since I can't see the audience, I don't, please feel free to interrupt me so I'm not talking into a vacuum. Yeah.
We will.
All right, great. Right. So so the broadest level, my talk connects with the theme of much current interest in many-body physics, namely the dynamics of quantum systems undergoing unitary time evolution. Okay, so here I'm thinking about isolated quantum systems very, very generally. So, this could be a system of spins, it could be a system of cold atom molecules that an experimentalist may prepare. It could be a black hole, right? There's a lot of interest these days in the dynamics of black holes. But in all these regimes, I'm thinking about a strongly interacting, highly excited many-body system. So I'm away from the ground state. I'm away from, there's no quasi-particles in the system. So usually a lot of the tools and techniques that we have for solving many-body systems, I'm away from all of those limits. Okay, so it's strongly interacting, highly excited many-body systems undergoing unitary time evolution. And in fact, I'm going to be thinking of the unitary time evolution quite generally. So one of the most familiar settings is, of course, time evolution that's generated by a time-independent Hamiltonian. So that's this top line here, right? And also think about blockade systems where the unitary is generated, where the Hamiltonian is periodic in time. So this gives you what's known as a blockade unitary, which is the time evolution operate over one period. And then the time evolution over n periods is by acting with that unitary multiple times. And finally, we can also consider time evolution generated by random unitary circuits. Okay, so this is a setting that has been receiving quite a bit of attention in recent years because it really provides us with a very solvable way of approaching many of these questions. Okay, so in this last case, what I want to retain about the dynamics is locality and unitarity, but get rid of all other structure. Okay, so one common setting for doing this is to have unitary gates act on my system, and the gates can be random in both space and time. So the only structure that you're maintaining is locality and unitarity. Okay. So that's kind of a general setting for what we'll be doing, and you can ask a variety of questions. A question that has been at the center of a lot of activity in recent years is whether and how reversible unitary time evolution can bring a system to thermal equilibrium at late times. Okay, so usually when we're talking about thermalization, you have a system. The system, if you open a textbook, right, and you ask about textbook statistical mechanics, you have a system. The system is coupled to some external reservoir or bath, and the system reaches thermal equilibrium at late times as a result of exchanging energy or particles with this bath, right? But in a unitary system, when your system's undergoing unitary time evolution in a closed quantum system, there is no external reservoir, there is no bath, right? And the full system as a whole always remembers all details about the initial condition, right? So you could prepare some very, very highly non-generic initial state, and in some detailed sense, the system will remember all information about that initial state for all times. Okay.
But can I ask a naive question?
Yeah.
Why do I need the adjective reversible? Isn't unitary time evolution always reversible?
Yes, that was more just for emphasis.
Okay, good. I thought I missed something. Good.
Right. Yes. Good. So so you can ask, given that all memory about the initial condition is always retained, what does it even mean for such a system to reach thermal equilibrium, right? And one way that we now have of understanding this is to look at local subregions within the entire system. Okay, so if you go in and you measure observables in some small part of the system, which is described by A alone, then does that subregion, look like it? Do observables measured within that subregion alone look like what you might get from a canonical Gibbs ensemble or some other equilibrium ensemble at an appropriate temperature, chemical potential, these other thermodynamic parameters that could be set by the conservation laws in your system and by the initial state. Okay, so when this happens, you say that the rest of the system is able to act like a bath for some local subregions. Okay, so the intuition here is just that even though all memory about the initial state is retained for all times, this information can get scrambled or spread out in very, very non-local degrees of freedom, right? And an experimentalist will never have access to such global measurements in any case. So if you go in and you measure some local subregion, it can look like the rest of the system is still acting like a bath for that local subsystem, right?
Is this just the usual statement that for certain systems, or in relative generality, any less than half the system looks approximately thermal?
Right, but then it again depends on which observables you're probing, which systems. It's certainly not true that this is going to be the case for all systems. Okay, so that actually brings me to my next. So before going there, I just want to give a brief condensed matter / AMO pitch, which is just that, even though these are very general abstract theoretical questions, they've really come into very sharp focus recently because of lots of advances in preparing isolated systems in a laboratory setting, right? That are really for long periods of time. They're very much protected from environmental decoherence, and they can allow us to study these kinds of systems in a variety of different platforms with different types of interactions, spatial dimensions. So you just have a lot of systems giving you a lot of different tuning parameters in which to study such questions. Okay. So coming back to this question that I was asking about whether reversible time unitary evolution can bring a system to thermal equilibrium at late times, there seem to be kind of two broad universal answers to this question that are generic. When a system is able to bring its subsystems to thermal equilibrium, we say that it's thermalizing, which means that the system in that case acts as its own bath and brings subsystems to thermal equilibrium. But a lot of excitement and effort in recent years has been devoted to a class of systems where this never happens, right? So these are the so-called many-body localized systems. So in the system, no matter how big you make it, it's strongly interacting, it's highly excited, you can make a really, really big system, but it's still never able to act as its own bath. So what that means is that in a many-body localized system, you can create some very, very weird non-equilibrium initial state, right? So in a spin system, you could create some very particular pattern of initial spins, like 5 spins are up, then some are down, then some are rotated in a little, way. So you can create some product state which has a very particular pattern of spins, and some local memory of that initial imprint will remain forever. Okay, so in that sense, you can say the system acts like as a quantum memory, if you will. And yeah, go ahead.
Is there any relation between the statement that it can't act as its own bath, and the statement that the total system can still reach thermal equilibrium, or do these many-body localized systems just never reach equilibrium?
These many-body localized systems never reach local thermal equilibrium.
Okay.
Yeah, so that's the point, that you can prepare some very weird initial state, and now you go in and you measure local observables everywhere, and it just never reaches, never relaxes to the value you would expect from thermal equilibrium.
No, locally sure, but even if I couple it to a bath?
No, if you couple it to a bath, then it will.
Okay, good. It's a statement about these local systems.
It's a statement about isolated quantum systems.
Okay,
so my entire talk, I'm just going to be focusing on isolated quantum systems. Yeah.
Nice.
So is the first statement the same as ETH, so like eigenstate thermalization, or is it?
Yes. Yes. So when a system is thermalizing, then it obeys the eigenstate thermalization hypothesis. And many body localized systems do not obey the eigenstate thermalization hypothesis. So if you go in and you measure local observables in eigenstates in a many body localized system, you'll see that from one eigenstate to the next, so states at the very same energy density, local properties fluctuate wildly from state to state. Okay. So if you're not familiar with these models, they're usually in systems which have a lot of disorder or randomness in the couplings. So the simplest, toy model, which is really trivial to think about, is just if you had a Hamiltonian, which was just described by hi sigma iz. Okay. So now this is just a solvable Hamiltonian. Every eigenstate is a product state of sigma z. Of course, the different states just have some random patterns, and that gives different states that enclose in energy very, very different local footprints. And the idea is just that if you start with these local fields being very, very strongly disordered, and then you weakly make your system interacting and add in hopping and all of this, there's a sense in which you can get a dressed version of the problem that still has these local conservation laws. Okay, so the reason this system never reaches thermal equilibrium is it's because it's described by these exponentially many emergent local integrals of motion. So these are operators that are conserved by the dynamics forever. So as a result of these conservation laws, it just cannot reach equilibrium because it's a very constrained system, right? But these are not conservation laws that you put in by hand. They're emergent in the sense that they come out from the dynamics. Okay, so it's not a fine-tuned model. There's a wide range of stability there. Okay, so good. So these are kind of two broad answers to whether a system can reach thermal equilibrium at late times. There's also, in the no category, there are also integrable systems which thermalize to what are known as generalized Gibbs ensembles rather than Gibbs ensembles. But these are usually fine-tuned in parameter space, and that if I perturb some integrable model, I generically expect to destroy the integrability, right? So, if you're asking about robust possibilities, there's broadly two answers, which is thermalizing and many-body localized. But it's actually a very open question in the field about what the full range of dynamical possibilities are, whether you can have intermediate possibilities between thermalizing and MBL. It's even a question about how best you should characterize the intermediate. What do we mean when we say that something is intermediate between thermalizing and MBL, right? Because at infinitely late times, it's usually one answer or the other, right, in an infinitely large system. But, is it possible, I'll get to one particular way in which it could be intermediate in just a second, but, it could be that, in the way a system reaches thermal equilibrium, some systems could just take parametrically longer than others, right? And how do we characterize that? How do we understand that? So this is again, a major question in the field about what's a full set of dynamical universality classes, if you will, right? So
you say universality, so you mean that this range in here it's not just a matter of, when I say that the system is thermalized, that's an approximate statement, and I just relax my tolerance and it becomes less and less approximate, and I get down to the no side. Like, it's not just a spectrum of how good your approximation is. There's some qualitative difference.
Right. So yeah. So at the crispest level, when I'm talking about yes and no, I mean that you have an infinitely large system that you're looking at infinitely large times, okay. And does it thermalize or does it not, right? But now, so one particular way in which something could be intermediate is you could ask the question whether all initial states reach thermal equilibrium at late times, right? And of course, this is only sensible for by all. There should be like an asterisk there. By all, I mean all initial states which have kind of for which thermodynamic observables like temperatures or chemical potentials or energy densities can be defined, right? So you want your states to have sub-extensive uncertainties in conserved quantities, right? So you don't want the fluctuations in energy to be as large as the expectation value of the energy, because then you don't even know, well, what temperature should you stick in there, right, for it to thermalize. So, for instance, if you have these global superposition or cat states, right, then those can be problematic. But ignoring those, usually when people are talking about thermalization or ETH, they have in mind some class of what's known as short-range correlated initial states, for which all local densities can be properly defined, right, and they have a meaningful expectation value for those. And for this entire class of states, you can ask, is it true that every single state of this kind that you prepare does reach thermal equilibrium at late times? Okay. And if that's true, that implies what's known as a strong version of the eigenstate thermalization hypothesis, which tells you that every single eigenstate of your system must be thermal. Okay. So here I have some plots from from this paper, and this is just numerics from one of my papers, where I'm doing the usual tests that people do for ETH, which is I'm measuring some observable. On the left side, it's a local spin observable. On the right side, it's the entanglement entropy, half-chain entanglement entropy in every single eigenstate of the system. And on the x-axis, what's plotted is the energy density of the eigenstate. Okay. So what the eigenstate thermalization hypothesis tells you is that every single eigenstate individually looks thermal, right? So that all these expectation values, they become a very smooth function of the energy density, and fluctuations in these expectation values from state to state actually go down with increasing system size. Okay, so the black here is the larger system size, and you can see it's just becoming this very narrow band, which agrees with what you would expect from a thermal Gibbs ensemble at this energy density. That's what this value would agree with. Okay, so there is numerical evidence for this in certain spin systems, but the answer to whether systems that are thermal must obey the strong form of the eigenstate thermalization hypothesis is not known in full generality, right? And in fact, what's true is that even if you have a vanishing set of eigenstates in your spectrum that don't obey the ETH, right? This is still enough to have very measurable signatures in the dynamics, because you can prepare some initial state that has large overlap on that set of eigenstates. Even if it's measure zero in the full Hilbert space, you can still prepare initial states that have large overlap on those eigenstates, and then these would show you dynamics that look non-thermal. Okay. So, right. So this question about whether all eigenstates must reach thermal equilibrium, this was brought into sharp focus recently due to a set of very intriguing experiments that were done in a system of Rydberg atoms in a experimental group at Harvard. Okay. So what this group did is it's a spin system. I'll describe it in a second. But they prepared an antiferromagnetic initial state, which is kind of spins anti-aligned like that. They evolved it for some time t, which was set by the experimental timescales, and they measured some local observable in this system. Okay, and what they observed is that, well, as they're doing this evolution, this local observable is actually showing oscillations for a very, very long time. And it was actually oscillating about a non-thermal value. It's not that it's oscillating about the value you would expect from thermal equilibrium, right? So it was showing oscillations, and it was about a non-thermal value. But then they prepared a different initial state, which was all the spins pointing down, and this just rapidly evolved to thermal equilibrium. Okay, so this was very puzzling.
What's DW?
Sorry?
What's
domain wall density. It's just an experimental observable that they were measuring. Okay. But other initial states thermalized rapidly. Okay. So one thing that you might have expected is that, maybe this was just, maybe these different initial states were just at different temperatures. So why do you expect their behavior to look similar? But actually what was striking about the experiment is that, you can derive some kind of effective Hamiltonian governing these dynamics, and both initial states are at infinite temperature with respect to this effective Hamiltonian. Okay, so you have two infinite temperature initial states. One of them evolves rapidly to thermal equilibrium at infinite temperature, while the other seemingly seems to oscillate forever about some non-thermal value. Okay, so this again is an example. So these dynamics, they are in a dynamics in a constrained system, right? In this setting, the constraint is actually coming from what's known as a Gridboard blockade. Okay, so it's easiest to think of this Rydberg chain as just, you have a chain of atoms, And every atom basically has two, we just think of them as having two states. There's a ground state, which will be denoted by a spin down, and a highly excited state, Rydberg state, which will be denoted by a spin up, right? So then you have an effective spin 1/2 degree of freedom on every site. And these atoms are interacting with each other via strong van der Waals interactions. And what that gives you is actually an effective blockade, okay? Which means that if you have two spins that are both in this Rydberg excited state next to each other, they interact extremely strongly, and that gives you the strong energy penalty. So you actually, it's just cleanest to work in a constrained space where no two nearby spins are allowed to be up next to each other, okay? So this actually ends up giving you a very special kind of Hilbert space, because you no longer have a local tensor product structure, okay? So if you have two spins that are both down, right, then if you have two spins that are down, then the spin that's in between them can be either up or down. It's not constrained in any way. But if one of the spins is down, then the spin that's next to it is forced to be down. Okay, because of this Rydberg blockade, you can, or one of the spins is up, then the spin that's next to it is forced to be down. Because of this Rydberg blockade, you can't have two spins next to each other that are up. Okay, so anyway, we don't need all the details of this system, since that's not going to be the main point of my talk. But essentially the point is that, you know, in this Hilbert space, you don't have a Hilbert space dimension that grows as 2 to the L, but actually grows as like some Fibonacci number to the N. And you can define spin operators within this projected space, right? So these usually take the form of, if you go in and you flip some spin, you can only do it if it's allowed by the constraints. Okay, so that's what this X tilde operator does. So it's like, if you have in this bottom line, this flipping this middle spin here from down to up would lead to a violation of the constraint. So it just doesn't do anything on this state. While if you can flip the spin while still remaining within the constraint space, then that's fine. Okay. So a model Hamiltonian that was written down to describe this experiment was actually extremely simple. It was just this dressed sigma X operator, which says flip a spin if the two neighboring spins are down, otherwise don't do anything. Okay. So if you didn't have the constraint, this would of course be a trivial system that's just exactly solvable, it's integrable. But in the presence of the constraint, this actually becomes a highly interacting Hamiltonian that is expected to thermalize generally, because there's nothing, it is strongly interacting, it's not non-interacting, so, and it's many-body, right? So, right, so under this idealized model, you can again do numerics of the, you know, that try to simulate what was done in this experiment, and you again see that yes, some set of initial states actually thermalize rapidly, which is this red line, while others seemingly oscillate forever. Okay, so right, so what's going on here, right? And there was a intriguing phenomenology that was proposed to describe these experiments, which was, you know, which said that, okay, the way to think about them is that in these constrained systems, your many-body spectrum actually has what are known as many-body scars. Okay, so there isn't really you know, this is trying to appeal to to terminology from dynamical systems, but you know, there isn't really a crisp definition yet of what many-body scars are. But loosely speaking, there's some measure zero set of ETH violating eigenstates that can be interspersed with thermalizing eigenstates. Okay, so what this picture is showing you is the entanglement entropy versus energy again. And you can see that while the bulk of the eigenstates look thermal, you have all these different, you have this set of eigenstates here that have entanglement entropy that are far, far less than the thermal value. Okay, so it's really at the same energy density right here, you have both thermal and non-thermal eigenstates. And now if you prepare certain initial states like this Z2 staggered state that we were talking about, which was up, down, or Rydberg, ground, if you prepare this particular initial state and you look at its overlap with all these all the many-body eigenstates, you see that this Gridboard state actually has a very high overlap with this set of special states that look very non-thermal. So that's why dynamics in that state look non-thermal while others look thermal. Okay.
Do these special states survive in the limit where your system size becomes infinite?
Great question. So,
like if it's a boundary effect, basically.
Right. So for this particular model, the answer isn't actually known, but my strong prejudice is that no. Okay. So what my collaborators and I showed is that there's a sense in which if you just study this numerically, we don't have a complete analytic understanding of, so the main question actually is what causes scars. Okay. So, this is a interesting phenomenological description, but if you want to know whether it survives or not, you want to know, well, what's causing it and does that feature survive, right? And we don't actually have a full answer to what causes this in this particular model. My collaborators and I did show that this particular model looks numerically very close to an integrable point, okay? And that integrable point is, again, not one that's known. It was just something we found numerically. So it seems to be a new integrable point that we couldn't find in the literature anywhere. So, given that this is a slightly perturbed version of that, and we don't know what the exact integrable point is either, right? It's in this particular system, it is believed that as you keep scaling up the system size, this phenomena goes away. And moreover, that it's quite fine-tuned. Okay, so it's not the case that just having this kind of constrained Hilbert space is enough to give you scars, right? So you can take this model, and what's certainly true is that if you add weak perturbations to this, those are enough to destroy all of this phenomenology. Okay,
I have a question online. So these points 0, 1, 2, 3, 4, 5, 6, and so on. Like these you regard as remnants of integrability?
So that's again, this is not a settled question, and this is not the main point of my talk, but yes. So when you have an integrable system, you actually, of course, have a broad range of. So let me see if I actually have a figure here.
Well, maybe if you talk about it later, we can postpone it.
Sure. Yeah. So when you have an integrable system, you know that you expect to have a very broad distribution of entanglement entropies, right? Because you have all sorts of dynamical sectors, right, coming from the different conservation laws. So even though some states have the same value of energy density, they could have they could belong to completely different sectors because you have so many different conservation laws in your integrable system, right? So at the same energy in an integrable system, you actually have a broad distribution of entanglement eigenstate values. And what we showed is that, if you add a perturbation, a deformation to this model, and you tune that deformation, your system actually very continuously goes from looking like your whole spectrum looks non-thermal towards this value. And then as you deform further, all these states go away. Okay.
And these plots were generated using exact diagonalization for a small system?
That's correct. Yeah. So these are plots from this paper here by Turner et al. Yeah.
Okay, thanks.
Yeah. Exactly. So right. So in this particular case, A, we don't know what causes these ETH violating eigenstates, and B, this model appears to be fine-tuned. Okay. So 1, we don't know what causes it. 2, it probably doesn't survive in the thermodynamic limit, and 3, like generically, if you perturb it, all of this goes away. Okay. But this will not be true in this class of fractonic models that I'll get to very soon now. Okay. So one broad question is like, well, what causes scars, right? How do we think about scars? And there was one exact mechanism for generating scars that was provided by these authors that are Shiraishi and Mori a couple of years ago, right? So this is just, again, a family of kind of fine-tuned Hamiltonians where these scars can be embedded by hand, okay? So in this class of Hamiltonians, the scars do survive in the infinite size limit, okay? So what they do here is they have this Hamiltonian and they write it as, it has this form, okay? So the PIs are local projectors. So you have local projectors and then local terms HI that are sandwiched between these projectors. And then you have some other piece of this Hamiltonian, which is H prime, okay? So these local projectors in general do not commute with each other. but H prime does commute with all these local projectors, okay? So given that these projectors don't commute with each other, this model does not have any obvious symmetries, right? So usually when you think of a system as having local symmetries, it takes the form of being a sum of local operators or a product of local operators, right, to get a local unitary evolution for the symmetry once you exponentiate that operator, right? So because these projectors don't commute with each other, this Hamiltonian doesn't have any explicit symmetries. But nevertheless, if you look at the Hilbert space of this Hamiltonian, it ends up kind of fracturing, right? So this is this terminology that we were using in our paper. So you end up with this kind of dynamical or emergent fracturing of the Hilbert space into two subspaces. Okay. So what you can immediately see here is that if you have a set of states D naught, right, and this could have zero Hilbert space domain. This could just have, there could be no states in this set. But if you have some states D naught defined by the set, if you have this this emergent space D naught defined by the set of states that are annihilated by all these local projectors, okay, then this part of the Hamiltonian just doesn't act on those states. Only H prime acts on those states. And H prime is very, very special because H prime does commute with all these different local observables. Okay. So the set of states which are annihilated by all these projectors dynamically never mix with the set of states with the rest of the states. Okay. And because these states are annihilated by all these local projectors, they actually look like ground states or what are known as frustration-free Hamiltonians. So these states typically have very low entanglement. Okay. So, this Hilbert space, even though there were no explicit symmetries present at the outset, it dynamically fractures into these emergent subspaces. And these states in D naught have very low entanglement. And then by tuning the properties of H prime, right? I mean, the simplest thing is to just have H prime be zero, but you can, in general, give H prime, you can have an H prime that has some, that's non-zero, right? But by tuning H prime, the relative energies of eigenstates in this block can be tuned, relative to the eigenstates in this other block, okay? So in reality, the eigenstates in this block and this block never see each other, but if you just plot them in this, if you just, plot the many-body spectrum, then the states from this, as a function of energy alone, then the states from this will be completely mixed with the states from that. And so even though they're at the same energy, they can actually have very, very different entanglement properties, okay? So by tuning H prime, you can embed these low entanglement states anywhere in the spectrum by hand, okay? So, okay, so, so this is one particular somewhat fine-tuned way of getting these kinds of scars, okay? So, right, so this is one way of getting it. A lot of examples that people have been recently discussing in this class of systems actually is just variants of this construction by Shiraishi and Mori, but it also it doesn't obviously describe what's happening in this Gridboard PXP model, because that model actually is able to connect you from every eigenstate to, or every basis state to every other basis state. Okay. So this brings me to what I was saying about integrability, where we showed that this model is actually proximate to a new kind of integrable model. And integrable systems, of course, naturally have fractured Hilbert spaces because of all these different conservation laws, right? So if you just looked as a function of energy, there's lots of different sectors that just can't talk to each other, okay? So one question we want to pose is, what are other general and in particular robust mechanisms for getting some kind of emergent Hilbert space fracture, okay? And I want to focus on a particular class for the rest of this talk on the so-called fractonic models, okay? So these are models whose, right, so I'm going to present to you a class of systems that are inspired by fracton models, right? So these were models that were actually initially studied in the context of quantum information. And they're models whose dynamics look very, very glassy, okay? So they have elementary excitations like charges, for instance. that have restricted mobility, and I'll describe why that happens in a second, okay? But composites of elementary excitations may be mobile. There's lots and lots of work on them. Recently, there's solvable models in 3D. And there's a description for these fractonic models in terms of higher rank gauge theories, okay? And what these imply, this is some emergent gauge theory to describe these kinds of systems. And these imply, for example, that both charge and dipole moment should be conserved, right, in this class of models. So by using this by thinking about this conservation of charge and dipole moment, we were, sorry, this is not moving. Yeah. So you can consider a class of fractonic, so-called fractonic models in one dimension, which are inspired by these, these models that have been studied extensively in the quantum information side. And what we'll do is essentially just consider a spin chain again. But now we're going to demand that both charge and dipole moment are conserved, right? That's it. So I'm not imposing any other conditions on my system. The charge is this U1 charge, which I have a spin 1 on every side here. The values of z on each side can be -1, 0, or +1. I demand that the total U1 charge of this is conserved, and that this dipole moment is conserved, which looks like a sum over all sides. You have the x and you have z sub x, okay? So there's just two local conservation laws. And usually to get non-thermal dynamics or integrability, you need extensively many local conservation laws, right? So you need order L at least. Here, they're just two local commuting conservation laws. And what's remarkable is that with this, we can prove, right, analytically. So we're not relying on just numerics. We're not relying on heuristic statements. You can analytically prove that the presence of these two conservation laws alone and spatial locality is enough to give you exponentially many scars or exponentially many states that look non-thermal. Okay, so in this class of models, we'll again have thermal and non-thermal states interspersed with each other, but now we can understand why they happen, how robust they are, and in particular, as long as these constraints are obeyed, you can perturb your model however you want, and you'll continue to get these kinds of this kind of weird thermalization. Okay, so to understand why this combination of charge and dipole moment can give you very glassy dynamics, it's useful to just think about how would charges move under these constraints, right? So so suppose, as I said, we have a spin 1 on every side. You have 0, minus, and plus. So suppose you have a single plus charge interspersed in a sea of zeros, right? So this plus charge has a charge 1, and it has a dipole moment r if this charge lives on site r, right? But now if this charge tries to hop to the left or to the right, even though the charge will be conserved, your dipole moment changes, right? So this charge actually cannot hop to the left or the right, so charges are immobile in general. However, if you have a dipole, right, which is this minus plus composite or plus minus composite, then for this dipole, the charge is 0, but the dipole moment now becomes position independent, right? It's just in this particular dipole, the dipole moment is 1. And if you take this unit and you move it around, the unit as a whole is mobile. Okay, so even though charges are immobile, composites of charges like dipoles are mobile, and now charges can move by piggybacking on these dipoles or emitting dipoles. Okay, so in this particular case, you have this charge plus again, and you see that you can conserve your charge and dipole moment if this charge hops to the left but emits this dipole in the process, or you can think of it as having hopped to the right and emitting this opposite dipole in the process. Okay. So, right. So already, just by putting these two constraints in, you can see how the dynamics look quite restrictive. Okay. And to study this in more detail, you can consider various classes of systems, right? So we can have static Hamiltonians, where all the terms that appear in the Hamiltonian conserve charge and dipole moment. Or, as I was mentioning at the beginning of my talk, you can build unitary circuits with charge and dipole conservation. Okay, so now once again we have these circuits that are random in space and time. But for every local circuit, instead of just having it be a Haar-random gate that acts on 3 sides, we force it to be a Haar-random gate that acts on 3 sides, but conserves charge and dipole moment, right? So this gate actually looks block diagonal in the spin space because you're only allowing this gate to make transitions between states that have the same value of charge and dipole moment. Okay. So is there any questions about the setup here? Okay, good. So right. So now we can study dynamics with this class of circuits, and in particular, the circuits can be made random in space and time. So usually when you're thinking about many-body localization, that's a statement that requires you to have a Hamiltonian, right? If you make MBL or a flow case system, which is periodic in time, if you make an MBL system completely noisy in time, where everything changes from one side to the other, all your Hamiltonian is just stochastic, then that's not supposed to be compatible with localization. Okay. However, what we'll show is that for this class of models with Q and P conservation, you can actually add in this temporal noise, and this non-ergodicity persists. Okay. So to just give you to show you what this looks like, right? What I've done here is I've taken this kind of circuit, but I've made it periodic in time. So I still have eigenstates that I can talk of. These are eigenstates of the blockade unitary. I could also have considered eigenstates of a Hamiltonian system, but then you can start worrying about whether that's fine-tuned in some way because of just putting in certain interactions and not others, right? So I have a flow case circuit that conserves Q and P. I diagonalized it. I got all its eigenstates. It's a flow case system, so energy is not conserved. So everything nominally should just look like it belongs to infinite temperature. And in that circuit, if you resolve by your conservation laws, so this is Q equals 0, and each line here is a particular value of P. Okay, and there's L squared different values of P. There's order L different values of Q. So there's order L cubed different sectors, right? These are explicit symmetry sectors that I put in my hand. So within each explicit symmetry sector, you would expect that the dynamic should just look thermalizing, which in this case means thermalizing at infinite temperature. There should be nothing special. Once you've put in all the conservation laws in a flow case system, everything should look the same within that sector. However, what this plot shows you is that if you measure the entanglement at a given value of Q and P, you actually get this very, very broad distribution. So if you look at Q equals 0, P equals 0, you can see that the entanglement of eigenstates has this broad range of values that it takes, right? Even within a given sector. So this is very much like those scars that we were looking at, but at an extreme level, because you can see that it's extremely broad. You don't even see this kind of thermal bland with a few exceptions, okay? So we want to understand where this might be coming from, and so what we are able to show in this problem is that the reason this is happening is that your Hilbert space is again fracturing into exponentially many emergent dynamical subspaces. Okay, so you have only order L cubed explicit subspaces given by the symmetries, right? So that's by each Q and P sector number. But now if you go within the sector labeled by a given value of Q and a given value of P, you see that your Hilbert space within that sector actually fractures into exponentially many emergent dynamical subsectors. So these are all different blocks within a given sector that never talk to each other dynamically. Okay, so this is phenomena that's reminiscent of both MBL and scarring. It's reminiscent of MBL because we'll see that there are some particular states here that are exactly localized. You can prepare that state and it remains in that state forever. And it's of course reminiscent of scarring because you have this broad distribution of observables within a given symmetry sector. Okay, and these L bits are these local integrals of motions that I alluded to earlier with MBL. Yeah, these emergent conservation laws. So you can get, there's a sense in which you get L bits in the system, but it's kind of state dependent. and you can get the strict localization even without disorder. Okay, so you don't have to put in spatial disorder in the problem. You can make it translationally invariant. You can make it random in time, but you still get these kinds of localized states even without disorder. And the most important feature about this is that it's robust, right? All I need for this to get this phenomena is charge and dipole conservation and locality. Okay, so with these other models that we were looking at in that Gridboard chain, this PXP model and so on, it's definitely not robust. And you know that it doesn't survive in, for large sizes and all of that. But here it's completely robust because it's coming entirely from these symmetries. Okay. So how do we understand what's going on, right? So it's actually really easy to see that just the combination of these two symmetries gives you exponentially many strictly inert states, okay? So these are product states that you can prepare that are left invariant by the dynamics, regardless of the randomness in the dynamics, regardless of spatial or temporal randomness in the dynamics, okay? So to understand that, let's again think of these circuits, but let's give the circuit some finite spatial range M, okay? And then what you can see here is that let's take the system and divide it up into chunks of size M, okay? In every chunk, you can go in and randomly put down either plus charges or minus charges, right? All the charges in the chunk are either locally all plus or all minus. But then when you act with your circuit on such a configuration, the gates of your circuit, they either fall in this block, right, which is locally all plus. But if it's locally all plus, then on this three-side system, this locally has maximal charge, right? So there's no local rearrangement you can make on these three sides that will preserve the charge, because plus 3 is as high as it can get, right? So your gates will either completely lie within this block, or they'll straddle two blocks and have a single domain wall between minuses and pluses in there, right? So now if all you had was charge conservation and you had such a gate which was minus, minus, plus, then of course the net charge of this little block is -1, and there's many rearrangements that you can do that preserves the charge. Okay. But given this particular charge of -1, the configuration which packs all the minuses to the left end and pluses to the right end is a configuration of maximum dipole moment given this particular charge, right? So now if you want to try to make rearrangements here, what you'll find is that you can make charge respecting rearrangements, but they'll necessarily change your dipole moment. So anytime you act with a gate on such a configuration, you can't ever do anything without locally violating either charge or dipole moment. So this configuration is just strictly inert. It can never go anywhere, okay? And it's obvious to see now that there's at least 2 to the L over M strictly localized states, right? Because you've divided your system into M chunks, and you've on each one you've put plus or minus. So as long as your range, right, the range of your gates or the range of your Hamiltonian is finite, there's exponentially many such states. Okay, they're a vanishing fraction of the full Hilbert space, which scales as 3 to the L, but these states always exist. Okay, and what's more is that of course, in such states, you have state-dependent local integrals of motion, right? So in this particular state, the charge on every site or on every block of sites is locally conserved. Okay. So this construction is very general. It just shows you these states exist. This is, of course, a very loose lower bound on the number of such states. Actually, you can, if you go in and you numerically try to search, and we have a different, I won't get into that, there's a different recursive algorithm that you can use to exactly count the number of states that exist for any size of gate. And you can see that, these are scaling exponentially, and the number, which is 2 to the L, is actually, for 3-side gates, is actually much larger than what you would have estimated from this lower bound. Okay. Good. So then these are states that are strictly inert. What you can also do is then you can build up, so you want to build up this fractured Hilbert space with all these different, so there's all these different emergent subsectors, right? And there's a number of states in each subsector. So I've only described to you the subsectors that have exactly one state, which are these strictly inert product states. But you can see that you have this huge variety of emergent subsectors with lots and lots of this wide variation in sizes, right? So you can build this whole thing up by actually starting with locally active regions, right? So these are regions that are not inert. They have lots of, things are dynamical here. But then you can embed these active regions in between inert regions, okay? So how that works is, you can start with this inert background, state of the kind that I just described. Then you can go in and you can embed some little active patch. So this is a patch that locally, so if it's all zeros in that, if you have 4 side gates and you just have a sea of zeros, you can pop in these anti-aligned dipoles, which look like minus, plus, plus, minus, then your dipoles can move around. So in general, it's easy to construct kind of active regions, especially once your gate size is large enough. So 4 or larger is sufficient, right? So you create this active region, but now what you can do is that you can shield an active region of any finite size by putting minuses to the left of the active region and pluses to the right, or vice versa, right? Because what ends up happening is that you have these shielding regions, and in this active region, your system tries to grow, but anytime it does that, it melts the shielding region, right? And in doing so, it either moves a plus charge to the left or a minus charge to the right, but then that increases the dipole moment, right, of this region, because you're moving either plus left or minus right, or decreases the dipole moment. So as this active region starts trying to melt these shielding regions, it actually becomes less and less active because it keeps lowering its dipole moment. Okay, and eventually, if your shielding regions are at least as large as your active region, all the stuff that was happening can remain localized to this region, and your inert states can be left inert, your inert regions. Okay, so this is a way of, within a given state, right? So you don't even have to look across different states. Within a given state, you can have some regions that look like, if you can start with some local spin there and it decoheres, or it just relaxes to some non-zero value. But you can protect some states that are away from this region against decoherence by just shielding this active region. Okay, so this is another sense in which locally, whatever quantum information you had on these regions here can be protected against the activity in some other region. Okay, so what I'm showing you here is a plot of just a local observable z of x and t as a function of x and time. And I started in some configuration which I knew would be active in the blocks here, then they'd be inert on the edges, and then I made some shielding regions. And you can see that as I evolve in time, there's this whole region here that just fluctuates a lot, and spin in this region is close to 0, right? Even though I started with some polarized initial states. But then by the time you get to the edges of this chain here, these edge spins are not disturbed at all. So, this started as plus and this remains plus forever. This started as minus and it remains minus forever. So by doing this, right. So by doing this, you can actually build up subsectors of all possible sizes, right? Because you can just keep embedding different active regions between inert patches, and then you can have an inert patch and another active patch, an inert patch and another active patch. So in doing this, you can build up these subsectors of all sorts of sizes, and these are kind of determined by the Hilbert spaces of all these active regions that mix between each other, right? That are embedded into some starting inert patch, right? So, right. So here I'm just showing you the distribution of subsector sizes for 3-side gates and 4-side gates. And there is this interesting difference between 3 and 4-side gates, which has been called strong versus weak fracturing. And what happens with 3-side gates is that your subsectors fracture so much that if you go in and you look at the size of the the maximum emergent subsector size that you get, right? That's a vanishing fraction of the largest QP sector, right? So the largest QP sector size is roughly 3 to the L, because you're just correcting it by this polynomial amount, which is L cubed. But then within a given QP sector, if you go in and you ask how large your emergent dynamical sector can be, which is something like here, for 3-side and fewer gates, it's a vanishing fraction, but for larger than 4-side gates, these dynamical subsectors in the largest sectors actually scale in the same way, the size of these as the main as the size of the actual symmetry sector. Okay, so this gives you less severe fracturing, which has consequences for dynamics again. So good. So so what I've shown you is that just the conservation of Q and P gives you both strictly inert states and a mechanism for building up emergent Hilbert spaces of all possible sizes. Okay, so now you can say that, okay, this actually explains to a large degree why within this QP sector we had this wide variation in entanglement, eigenstate entanglement. Okay, because, well, you had eigenstate entanglement, but it shouldn't take a value that's appropriate to the size of this largest QP sector, but in fact appropriate to the size of the emergent subsector within that QP sector, right? So I don't know if you guys know what the page value is. It's just a measure of the entropy of, given a particular Hilbert space size, you can compute what the maximum entropy for that should be. And here there's a bunch of different dynamical subsectors. You have the entanglement within that, and you can see that the entanglement roughly follows this page value for the subsector sizes, but there's still this wide variation. And this further wide variation is coming from what I was telling you about here, which is that there's a lot of variation in spatial cuts as well, right? So you can have a given sector which belongs to a subsector by embedding an active region, then inert, then active, then inert. But within this state, if you go in and you cut somewhere here in the middle of an active region, the entanglement is going to be upper bounded by the size of the active region that you make your cut in, right? For that same sector, if you went in and you cut in the middle of an inert region, then your entanglement entropy is 0.
So, sorry, this black curve, straight line on where we're plotting the entanglement is just the entropy of maximally mixed state of
this subsector size. That's right.
Okay.
Yeah, exactly. So, but the point is that it doesn't even get to the entanglement of the maximally mixed state within that subsector size, because now there's all this cut-to-cut variation, right? So even though your state belongs to a subsector of some particular size, it could just come from the fact that you had lots of inert patches interspersed with active patches. And if you made your cut within an inert patch, well, then you get 0, which is, this guy here, like, the entanglement can be 0, even with a subsector there, right?
And how would the thermal expectation value look like? Or
sorry?
And how about thermal like if you would calculate the fundamental entropy in the thermal state?
Right, and in the thermal state, it would just be, so this is within the largest QNP sector, right? So the thermal in the thermal state, it would actually just be, so this is the emergent dynamical subsector, right? So if you were just doing thermal states, then you won't even be thinking that you have these emergent dynamical subsectors, right? Because then you're like, okay, you just have 2 conservation laws, which are Q and P. So you just expect it to be maximal here, determined by the size of the whole subsector, which is over there.
Oh, okay. Very good.
Right, but now you have all these subsectors, and this is the thermal value within a subsector, which is explaining a lot of the variation, but it's still not enough to explain the full variation, because you again have all these different ranges of block sizes within states and within a subsector. So it's just, everything is just really, really, I think, that's why we were using the word fractured, like, your Hilbert space is just divided up in so many different ways. And when you make a cut, it just cares about, well, locally, what little block are you sensing, right? So, this also shows up in entanglement dynamics, right? So here this S page is again this maximally mixed threshold, and you can compute, you can just start with some random product state. So now it's, it's not a Z product state, which could be inert. Just point your spins randomly along any direction on the block sphere, evolve it in time, and you actually see there's this big difference between 3-side gates and 4-side gates that comes from this degree of fracturing that I was telling you about. With 4-side gates, because if you start with this random product state, most of its weight lies in this very large subsector, which actually scales with the size of the symmetry sector. And you can see that, with increasing system size, the value that you saturate to is fairly close to the maximum value. But, I don't know if it actually exactly gets there, because, there is this deficit and it's only a very weak flow with system size. But for the 3-side gates, which have the strong fracture, you definitely don't get to the maximum value. Okay, so you can just start with some initial state that has overlap. If you expand the initial state, it has overlap across all these different dynamical sectors. But because these sectors are so divided and subdivided, this entanglement actually never gets to whatever maximum value it could be. Okay, so
sorry to interrupt. I know we started a bit late here. Do you think maybe another 5 minutes?
This is my last slide, actually. This is my last slide before the summary. Yeah. Okay. And then, all of this can actually also be generalized to higher dimensions. So, if you have 2 dimensions, and instead of just doing charge and dipole moment conservation, you can actually do quadrupole moment conservation. And then you can get kind of similar pictures for large numbers of inert states, embedded sectors, fracturing in 2D. You can actually realize all of this in an experimental setting, because you can apply kind of large tilted fields and weird potentials to generate these kinds of dipole conservations and quadrupole conservations. All of this can actually be seen in near-term experiments. So I just want to summarize with some, give a summary and some open questions. So the summary is that there's lots of rich physics in the dynamics of constrained systems. The twin constraints of charge and dipole moment plus locality provably gives you exponentially many Hilbert inert states, and shatters or fractures your Hilbert space into all these different dynamical subsectors. And this is a kind of localization which doesn't require spatial disorder, is robust to temporal noise, and it's potentially useful for this connection to quantum information definitely needs more fleshing out. But if you start in one of these inert states, or these inert states embedded in these, and shielded from these active regions, and whatever initial pattern you prepare in that local region will be preserved forever, right? So there's a sense in which that's a quantum memory. And there's lots of open questions. What are other mechanisms for Hilbert space fracture? So I already told you a little bit about higher dimensions and realizations. What happens if our models are not strictly local, but actually have exponentially decaying interactions, right? So if you have some finite range, then what happens? What happens if I softly violate these Q and P constraints? Are there connections to kinetically constrained models that have been studied in classical systems? So there's a wide variety of things we can study here. And yeah.
Thanks. I have a question about these. So these subsectors, when you say that it's dynamical, they're dynamic in the sense that they're evolving. Is the shattering itself also dynamic as the system evolves? Like, I guess I'm saying, is the number of these subsectors fixed, or is this also constantly changing?
Well, yeah. So what I mean by dynamical is that it's a shattering or fracturing of the Hilbert space that is visible in the dynamics. What it means is that dynamically you have a part of the Hilbert space that never talks to the other part, even though explicitly you didn't build in any conservation laws. Okay, so that's what I mean. What I mean is really that it's an emergent fracturing in the sense that you have regions of your Hilbert spaces that are never connected to each other under dynamics, but that there's no symmetry reason a priori to expect them.
I see, but the collection of these non-interacting systems is sort of fixed at the beginning. I guess what I'm asking is to what extent I can think of these as sort of an emergent superselection sector. Because
that's exactly what it is. That's exactly what it is. So once you fix your spatial range and if you fix QP and the range, then it is just a whole variety of emergent superselection sectors that were not present. Just if you only thought of Q and P, then you only have L cubed symmetry sectors, right? Or super selection sector that is symmetry. But now you get all these. So that's fixed at the beginning of the problem.
Okay, very cool. It's like a dynamic super selection sector.
Exactly. That's exactly what it is. Yeah.
Cool. Thank you.
So I have a couple of questions. So one is taken from Rose's question, which is just trying to still get my head around this fracturing of the limit. So in this quantum circuit picture, you mean that you construct this quantum circuit where the gates commute with Q and P, and then like you multiply all these unitaries together and you get the big unitary, and that unitary has a certain block structure.
Correct.
This is what you mean, right?
That's right. And the block structure of that bigger unitary, you might have naively expected there's only L cubed blocks because there's only L cubed labels for Q and P, right? So those are super selection sectors that come from the symmetry alone, right? But actually there's exponentially many blocks, not just coming from the symmetry alone. So that's the weird thing, that it's these dynamical super selection sectors where dynamically multiply that unitary, you just have blocks that can't talk to each other, and there's exponentially many of them.
Right, and then again, I think Rose was also trying to ask this, and then I wasn't clear from your answer. So the number of blocks that appear don't change with the size of, like adding more time steps to the circuit or increasing the size of the circuit, like spatially, that there's some dependence, or that there's no dependence on these?
Well, okay, so if you the time obviously matters, right? Because if you but let's say that for a fixed system size, right?
Okay. Yeah.
If you could run your circuit, if you make an infinite depth circuit for a given system size, okay, then it doesn't matter. But of course, if you just act with one layer of gates, then you know that all you can do is connect something with one layer of local gates. You can only mix something locally on the scale of 3 sites or 4 sites, right?
Right, but right. I mean, I was just talking about the scaling. So when you said that the fracturing is exponential, you mean with the number of time steps, or?
No. So let's get to the point where you've run your circuit to a time where if you have this Lieb Robinson or you have some light cone, right?
Yeah.
So once you run your circuit for a time that's at least as large as the system size. Okay. So then everything has had a chance to talk to everything else. Okay.
All right. Okay. So
once you're beyond that time, then you still have this block structure in your unitary multiplied out. Okay. And that block structure, by symmetry considerations alone, you would have expected that to have L cubed blocks, but it actually has exponentially many blocks. Okay.
Could you explain that? So what do you mean by, so why should it be L cube? I'm not missing that. So
right. Okay. So the L cube just comes from, so let's go back to, let's consider the case for a second of just charge conservation. Okay. So now you're acting
that's global charge conservation, right?
Global charge conservation, and it's implemented locally. So you're acting with local gates that conserve U1, right?
Yeah.
And they conserve U1 alone. Okay. So now how many different possible values for U1 are there in, say, a spin 1/2 or a spin 1 system of size L, right? So now you can go from minus L to L, right, for the number of charges. So there's order L possible values that your charge can take, right?
Yeah.
So there's order L possible symmetry sectors ranging from all up to all down and everything in the middle, right?
Yeah, right.
So if you start just with one layer of U1 conserving gates, then of course nothing much happens because you can only have locally only 2 or 3 sites talk to each other. But once again, I run my circuit out to a time that the butterfly cone has reached the edges of the system. Everyone's had a chance to talk to everyone else. And then if you keep running this, now you get a unitary that's block diagonal, right? But now it's block diagonal with order L blocks, right? So you can say all states which have total charge 0, which is, L choose L over 2 for a spin 1/2 system, have had a chance to talk to each other, and they all mix with each other. But the sector with all up, that has only one state in it, so that doesn't talk to anyone else, right? So if you just run this out, your big giant block unitary actually has order L blocks in it. Okay. Yeah. Good. So now let's do this with Q and P conservation. So now you again have order L possible values for the charge, right, which again range from minus L to L. But now you have order L squared possible values for the dipole moment. Okay. So the number of symmetry blocks that you might have expected naively, just thinking from a symmetry point of view, the super selection, is L cubed. So that's only polynomially many still. But actually you end up with exponentially many emergent blocks.
Oh, I see. But so does this depends on the choice of gates, or if I just choose them randomly subject to these symmetry constraints, I would always see this kind of fracturing?
That's right. So exactly. So you can choose them. So that's the part about it that's really striking, that it's not fine-tuned in any way, right? You can make it random in time, random in space, just pick these gates randomly from the Haar measure. And as long as you fix a given gate size, right? So the degree of fracturing depends on the range of your gates.
But what if I change the shape of the circuit, for instance? I mean, so the density of gates, for instance, right? Or if I play around.
All of that will change things. Yes.
It did. Okay, right.
Yeah.
Right. But you're saying for a circuit with a fixed shape, I randomly choose the gate subject to these constraints, I would always get this
exactly.
fracturing.
That's right.
And for a gate, for a circuit of depth, at least the system size.
That's right. I mean, you'll get even more fracturing if you look at circuits with depth less than the system size. But that's just because things haven't had a chance to talk to each other. Yeah.
Right.
Yeah.
Right. So just and then do you have an intuition of what's special about these particular symmetries? Is there some more general statement that if I have gates that commute with some other kind of symmetry, like what the symmetry? I mean, can it be any? And so clearly, it can't be for any choice of internal symmetries, right? I mean, so it seems to me that this dipole conservation seems to be a bit special because of this X dependence, right? So
that's right. So it is special. It's also this kind of, it scales super extensively, right? Because the possible values go from minus L squared to L squared. So it is a weird symmetry. I think the intuition is just that, even if you just look at the level of locally what your system is allowed to do, right? It looks glassy. Like this is what I was showing you, that, a charge can't really hop at all while conserving dipole moment. And you need to make this composite dipole object, and then the dipole can move around, right?
Yeah.
So I'm afraid I don't have an answer if you're asking, like, can I use this kind of, so I already showed you what happens in higher dimensions where you can do quadrupole conservation. I don't have an answer to whether I can, how to come up with a principle that would then generalize this to, what's the next kind of thing I should search for, right? Next set of symmetries that I should search for. So I don't have a great answer to that question, but yeah, I think the intuitive reason why this behaves so in such a special way is actually why these fractal models are glassy too, right? Because you just have all this very restricted mobility in your system. And yeah.
Right. And just one last question. So how do you impose dipole conservation at the individual for the individual gates? So for the charge conservation, you just kind of look at something like the total charge of the inputs is equal to total charge of inputs, right?
Right.
So you do something similar for the dipoles as well, but there's an X.
Right.
So do you just but you still have an X dependence, right? So each gate.
Yeah, so you have to choose an origin at the first time. So you have to choose an origin somewhere.
Along the spatial direction, right? And
that's right.
Each gate then comes with its corresponding range of X's, right? For which I have to satisfy incoming equals outgoing with those values of.
Exactly. And in fact, the way we do it, we don't even, you're just asking at the local level, right? So locally, you're just pretending like all you see is these three sites, right? For these three sites, let's fix the origin to be either in the center or the left edge or the right edge. It doesn't matter, right? And once you fix that origin, you can ask for these three sites, what rearrangements can I do so that your
I see. I missed that. So, but then in that case, how do you get dipole conservation at the level of the whole lattice? Because now each gate doesn't kind of like you need like at the level of the whole lattice, you would have X labeling from site 1 to 100, right? And your
No,
dipole.
that's right. But if it's locally, the local conservation is a stronger statement than the global one,
Yes.
right?
Okay.
Yeah. Yeah. So if locally your dipole is respected, it's going to also be respected globally.
So you are imposing something stronger than dipole.
Exactly. I mean, but that's usually the case when you're talking about, even if you're just doing U1 conservation and you're acting with like some local Hamiltonian, right? Then locally under the action of the Hamiltonian or the circuit, so you have some hopping term or you have some ZZ interactions. If you look within size 2 or 3, then you see that your charge is conserved, right?
Right. No, I agree with this,
Yeah.
but it is stronger, but also it kind of like about the previous comment. Like, I mean, then maybe having an extensive kind of a symmetry that it's probably not necessary. Like, I mean, this is really a local symmetry in some. It's not extensive. The one you're imposing.
No, but the fact that it's extensive is what's giving you the very constrained dynamics, right? Because I in the U1 case, I can again have gates that locally conserve U1, right? So it's again implemented at a local level, but then by the time you run your circuit out, you just get this block diagonal structure with order L blocks. Okay, so it's because just locally, if you think of this picture that I had, but like why can a charge not move, right? And that's because even whether you look at it locally or globally, because you have this position dependent conservation law, if you try to move that charge, you're going to change some quantum number.
Right. But that dependence is only within the range of the gates, though. I mean, so that is true that you still within the range of your gates there is some dependence, but a gate doesn't kind of know of the position within the lab it's acting.
That's correct. That's right. But even at the level of a gate, you can't move a single charge, right?
Right.
Yeah.
All right. Yeah. Thanks a lot.
Yeah. Okay.
Any other questions? Okay, so if not, let's thank the speaker again.
Okay. Yeah, no, thank you. Thank you very much for the interest in inviting me. This is really nice. Yeah.
Oh, our pleasure.